Okay, welcome to session 8. We are getting into the realm of what we call statistical inference. And to be able to do that, we need to discuss sampling distributions because we need to look at how samples are taken, right? So this is what we'll do in this session. At the end of the session, you should be able to explain why a sample is the only feasible way to learn about the population. Because sometimes you want to learn about the population, but you cannot use the entire population, but you need a sample. There are reasons why you should take a sample rather than examine the entire population. And then you should be able to explain methods of selecting a sample, and then you should be able to define and construct a sampling distribution of the mean as well as the proportion. The presentation is outlined this way. We'll look at the probability sampling distribution of the sample mean, and the sample distribution of the sample proportion. Now, we should take a sample for these reasons. It is physically impossible to check all items in a population. Sometimes the cost of studying the items might be prohibitive, or the contacting the whole population would often be time consuming, or some aspects of the analysis will lead to distraction. For example, if you manufacture bulbs, compact fluorescent lamps, and you want to be sure that it will last for, let's say, 1 month before it goes off. The only way you can do that is to light the bulbs for 1 month and see whether they will stay, right? And if you are a producer and you light all the bulbs that you produce, at the end of 1 month, you lose everything. So you can only use a sample. These are very good reasons why we take samples. And sometimes you can take samples in a probability sense. So we talk about what we call probability sampling, where a sample is selected in such a way that each element or person in the population being studied has a known likelihood of being included. Okay, so we want to be fair as possible. So sometimes you do what we call simple random sampling and all that. Now let's go on to talk about the sampling distribution of the sample mean. Now, generally, there are a large number of samples that can be taken. And when you take a large number of samples, you can compute a characteristic, or let's say a statistic such as the sample mean. And we're saying that this sample mean that you take will vary from sample to sample because it depends on who you include in the sample. So since the value of the sample mean can vary, it means that the sample mean itself, it's a random variable, and any random variable must have a probability distribution. So the probability distribution of a statistic like the sample mean is called its sampling distribution, right? So the sampling distribution of the sample mean simply is the probability distribution for all the possible values of the sample mean. It means that you list all the possible values of the sample mean and their associated probabilities. So for any given sample of size n, taken from a population with mean mu and standard deviation sigma, the value of the sample mean will vary from sample to sample. Let's illustrate this. Let's say that a class has only 5 students, and these students are Kofi, Ama, AC, Eric, and Mensah. Now we are going to code them. So when you see the number 1, it means it's Kofi, 2 is Ama, 3 is AC, 4 Eric, and 5 Mensah. Now this information is just telling us the number of hours they studied, in a particular week. So Kofi studied 22 hours, Ama 26 hours, AC 30 hours, Eric 26, and Mensah 24. Now, since we don't want to just study all of them, we want to take a sample. So we want to take a sample of just 2 students and see on average how many hours they studied. So we can take the samples as follows. It is possible to take the first and the second person when out of the 5, right? Kofi or Ama. But these are the possible combinations you can take. And you see that it is 1, 2, 3, up to 10. So there are 10 possible combinations you can take. So another way of doing that is to use the formula, the combination formula. So there are 5 objects, and we want to take 2 at a time. It will be 5 combination 2, and it gives us 10. So clearly, you see that there are 10, rows here, right? And we are saying that for each of them, if we sum the hours studied by the first sample, that is Kofi and Ama, they studied 48 hours in total. So for this first sample, the mean hours they studied is 24 hours, right? We can do it for each of them. Now, you see that some of the values are repeating. For example, 24 is repeating, but 22 is not repeating. So since we don't want to repeat them, we can put them in a probability distribution this way. So the numbers we actually saw in the previous table are 22, 24, 26, and 28. But 22 appeared once, 24 appeared 4 times, 26 appeared 3 times, and 28 twice. So we can find their relative frequencies, which is the same as the probability. So this will be 1 out of 10, 4 out of 10, 3 out of 10, and 2 out of 10. When you sum the relative frequencies, or the probability should be equal to 1, as we saw earlier. So nothing has changed, right? But we can do something. You see the sample means that we are fine. These are sample means, but we can find the overall mean. In other words, the mean of the sample means, right? To find the mean of the sample means, you just have to use this formula. Because 22 appeared once, you multiply it by its weight 1. But 24 appeared twice times, so you multiply it by 4. 26 thrice, so times by 3, and then 28 twice. And then you divide by the number of observations there. Okay, this is like summation fx over summation f, what we saw in descriptive statistics. So that gives it, because there are 10 observations, right? The mean is 25.2. But you see, the raw numbers we saw earlier for the 5 students too, we can calculate its mean. Because Kofi was 22, Ama was 26, AC was 30, Eric was 26, and Mensan was 22. So the 5 of them, when you sum and divide by the 5, you get 25.2. The 2 values are the same. The mean using the raw values and the mean using the sample means, you get the same value, right? So for the sampling distribution of the mean, we describe it by determining its expected value, or its mean, and its standard deviation, which we call the standard error. And you can see that for the sample mean, which is x bar, its expected value, or its mean, that is the mean of the sample mean, is always equal to the population mean, as we saw earlier, 25.2 and 25.2. But its standard deviation, or what is called the standard error, which we call sigma x bar, is equal to the population standard deviation divided by the square root of the sample size. Because we expect smaller variation in the sample means compared to the individual values in the population, right? So this is it. So an example. Now suppose the mean of a large population of measurements is mu equals to 100, and the population standard deviation is sigma equals 15. Then if you take samples of size 36, the expected value and the standard error of the sample mean is simply the population mean, right? Because we're saying the expected value of the sample mean is equal to the population mean, so it must be 100. But its standard deviation is the population standard deviation divided by the square root of the sample size. So it should be 15 over square root of 36, and it is 2.5. So you see that the standard error or standard deviation of the sample means is smaller than the standard deviation in the population. So if a statistic such as the sample mean, if it is drawn, the samples are drawn from a normally distributed population, then we expect that the sample mean will also be normally distributed, and they with a mean of mu by the variance of sigma squared over n. So for example, if samples of 50 women are chosen and the mean height is computed, we expect the sample mean to be normally distributed with a mean of 166 centimeters and then a variance of 40.32 divided by 50, right? Now, the formula for the standard error that we saw earlier, it's used when the the sample is taken from a population that is said to be infinite. In other words, the sample size is just a minute fraction of the population. But where the sample size is 5% or more of the population, we correct the formula of the standard error with this. So this is what we got earlier, sigma over square root of n, but we also multiply the result by square root of n, bigger capital N minus small n over capital N minus 1, where the capital N is the population size and the small n is the sample size. So this is the correction. Now, once we know that the sample mean also has a probability distribution, what we call this sampling distribution, and it is normal when the samples are drawn from a normal population, it means that we can also calculate probabilities for the sample mean, right? So again, since we've gone through the process, all you need to do is to do the z. For example, we want the probability of drawing a sample of 50 women whose average height is greater than 168. So we're saying that the sample mean is greater than 168. So to find your z, it is a sample mean minus the population mean over the standard error. You see, the standard error can be written in two ways. You can write it as sigma over square root of n, or you can also write it as square root of sigma squared over n. Now, if you take this one out and the square root sign affects it, it becomes sigma, right? So nothing changes. So since we know that the height of women is normally distributed with a mean of 166, then we subtract 166 from 168, divide it by the variance divided by the square root of the variance divided by the sample size of 50, gets 2.23. What it means is that we want the probability that z is greater than 2.23, or we want the area under the curve to the right of z equals 2.23. So we just read from the table. So it's the same thing as saying that we want the probability of z greater than 2.23. And the answer is 0.0129, because you can read this from the table. It's 2.23, so it is 2.3, right? 2.3 under 0.3. And it gives you this, right? It gives us 0.4901. But this is from 0 to what? 2.323. Okay, 2.23, sorry, it is actually 0.4871. So subtracting 0.4871 from 0.5 should give you the answer we got earlier, 0.0129. So nothing changes as we illustrated earlier. Now, we've been assuming all along that the population is normal. But if the population of the variable that we are interested in is not normal or is non-normal, but the sample size is large, let's say 25 or more, then it is true that the sample mean that is obtained will be normally distributed. And this result is a key result called the central limit theorem. So even if samples are drawn from a population that is not normal, but if the sample size is large, 25, we expect the distribution of the sample mean to be normally distributed. Okay, so this is an example. Let's say that an auditor takes a sample of 50 accounts receivable to audit. The mean value in the accounts is 200 and the standard deviation is 45. What is the probability that the sample mean will be less than 190? Now, nothing has been said about whether it's normal or not, but we know the n is large, greater than 25. So we can assume that the sample mean will be normally distributed. And then to calculate normal probabilities, you just have to convert to the equivalent z, right? Which we saw earlier as x bar minus mu over sigma divided by root n. So since our mu is 200 from the question, our sigma is 45 from the question, our n is 50, we want to find the probability that our sample mean x bar is less than 190. So it is x bar minus mu. So it's 190 minus 200 divided by 45 divided by square root of 50. It should give you minus 1.57. Now this same thing is the same. This is the same as saying that we want the probability that z is less than minus 1.57. We read from the table as we've illustrated, and the answer will be 0.0582. Now let's move on to look at the sampling distribution of the proportion. Now, so we looked at the sampling distribution of the mean, but then the proportion, because the proportion is also a useful statistic. Sometimes we're interested in the proportion, okay, of the population or the sample that have a particular characteristic. So this example I'm citing is saying that we may be interested in the proportion of drugstores that sell a particular drug. Okay, so we're saying that assume we have a population of 1,000 drugstores, and then a sample of 40 is taken, of which 32 sell a particular drug. It means that our sample proportion, p, small p, is equal to the number with that characteristic, which is the 32, divided by the sample size, and it is 0.8. What it means in essence is that 80% or 0.8 of the sample sell that particular drug. But we also have what is called the population proportion, denoted as pi, and it's equal to the number in the population with a particular characteristic divided by the population size. So just as we saw with the mean, the sampling distribution of the proportion is described by looking at its expected value and standard error. And the expected value of the proportion, or the expected value of the sample proportion, should be equal to the population proportion. And then the standard error is obtained by this formula: square root of pi times 1 minus pi over n. Where you don't know the pi, that's the population proportion, then the sample proportion is used. Let's take an example and calculate probabilities, just as we saw with the sample mean. So let's say that it is known that only 70% of drugstores sell a particular drug in Ghana. A sample, so it is known, that's the fact, so that's the population, right? Proportion. A sample of 40 drugstores is selected. Find the probability that more than 32 sell this drug. Now, 32 of 40 is 0.8. So the sample proportion is 0.8, right? So what we want to do is to find the probability that the sample proportion is greater than 0.8, given that the population proportion pi is 0.7. So you need to convert to the z equivalent. Z should be equal to p minus pi over the square root of pi times 1 minus pi over n, as we saw earlier, because the formula of the z is the same. The value of the random variable minus the mean divided by the standard deviation, right? So this will be p greater than 0.8, simply means that p greater than 1.38. So we want to find the probability of the area under the curve to the right, or the area under the curve to the right of 1.38. When you read from the table, as we've been doing, your answer will be 0.0838. So this is where we end sampling distribution, and it is giving us a background to be able to do what we call estimation, point and interval estimation. I'll see you shortly.